be focusing on rapid prototyping and additive manufacturing for manufacturing and industrial automation. And this is brought to you by Live Lab Learning. Live Lab Learning is a subsidiary of Academic Corp, a wholly owned applied software company created to provide world-class training to building, design, and engineering professionals. And my name is Tiffany Bjerken, and I am glad to be your moderator today. Throughout our presentation, we encourage you to interact with us by typing in questions and comments, and you can do that by using the questions pane. We will be answering questions at the end of the presentation, and we would love to have you connect with us in the future and keep the conversation going beyond today's event. We will be following up with you all in a week or so, and also we are recording today's session, and we'll make the link to the recording available to you very soon. And lastly, if you haven't already, search for our Live Lab Learning on Facebook and like our page to receive more training opportunities. So let's go ahead and get started. So you can please join me in welcoming today's speaker, Daryl Leah. Daryl is the Southeastern Sales Manager, 3D Production and Professional Printer Solutions for 3D Systems Corporation. For over 25 years, 3D Systems has revolutionized product development through the application of SLA, which is Stereo Lithography, SLS, which is SLS Systems, which is Selective Laser Sintering, and DMLS, which is Direct Metal Sintering, production 3D printers to generate concept models, precision and functional prototypes, master patterns and molds for tooling, and real end use parts. Our customers have helped us push the boundaries of what's possible with production 3D printing, and the results are well worth the effort. So Daryl, thank you for joining us today as our speaker, and I will pass it over to you.
Thank you, Tiffany, and everyone at Applied Software for giving me this opportunity to talk about 3D printing and how it can have a positive impact on manufacturing companies and industrial automation companies. Some of the topics and objectives of our discussion today will be discussing the benefits of 3D printing, and in particular how it impacts additive manufacturing. We'll do a broad overview of the range of technologies available and some of the primary applications for manufacturers. But we'll focus most of our time today on what we call production systems, and that would be stereo lithography, selective laser sintering, and direct metal sintering. But we'll also talk about a concept that we call at 3D Systems, reimagining the engineer's desktop, and that's incorporating scanning, modeling, printing, and inspection into your product design and also into your manufacturing processes. These really are, or truly are, exponential times in the world of 3D printing and in additive manufacturing. Our CEO likes to say that it's redefining Moore's Law. As you may know, Moore's Law says that technology will double in terms of processing capability every 2 years. Well, we're seeing that in the 3D world as well, if not at even faster rates. So some of the factors accelerating that are the benefits of 3D printing, which is reducing your research and development spend, accelerating your time to market, giving your designers the ability to create more complex parts, democratization, which is essentially opening up manufacturing opportunities to people that would never consider entering the space previously. And also, 3D printing is a very sustainable process, unlike traditional manufacturing methods, and we all know that the goal of many companies is to reduce their carbon footprint, and this gives them the opportunity to do that. Now, in general terms, the 7 benefits of 3D printing: faster time to market. So you're able to shorten your design cycles by giving yourself the opportunity to do multiple iterations of design and actually giving your designers the flexibility and convenience of creating models. By giving you the ability to create those models, you have improved communication throughout your organization. You're able to feel, touch, and see these concepts and actually improve your decision-making process by being able to refine your designs and get to manufacturing quicker. You're able to have more ideas and more breakthroughs, but ultimately by the ability to go through the concept to manufacturing process faster, and also the ability to create some parts and some geometries that you were never able to do before with traditional manufacturing processes. You're actually improving your product performance and quality. I want to talk to you about the available printing technologies that we have today and where they kind of fall in the spectrum. Polyjet printing, or what some of our competitors or other people in the space refer to as fused deposition modeling, gives you the ability to create early concept type designs. And the same would apply for film transfer imaging. These both are desktop type units. Kind of ties into what we'll be ending with today with the engineer's desktop. But these are printers that are office friendly, that your designers could literally have on their desktop to do proof of concept, early design concept type of projects. The next series of printers are what we refer to as our professional series. So once you're further along in your product design, you're able to get functional, highly detailed, form-fit type of models. The first, color jet printing, gives you the ability to print in two media. One would be a gypsum-based media, and the other is now a acrylite plastic, but you're able to print in full color. Some of our machines actually have the ability to print in true Pantone colors, up to 6 million different colors. The next technology is multi-jet printing. This gives you the ability to print highly accurate, true to CAD plastic parts that are great for form, fit, and function prototyping, and actually some limited use as well. On the bottom, and what we'll be focusing on today, is what we call our production systems. One is Stereo Lithography, SLA. The other is Selective Laser Sintering, SLS. And finally, we have the ability now to produce fully functional metal parts that are equal to, if not better than, casted or forged parts. Now, some of 3D printing and additive manufacturing applications. One, as we talked about, is general prototyping. Another is direct manufacturing. This picture on the top is off of our 5500X multi-material, or some people refer to as digital material machine. So this is actually one part where we're able to use a rigid ABS white plastic or ABS-like plastic and an acrylic fully clear like plastic for proof of concept and limited functionality type prototypes. Direct manufacturing, these parts were built on our SLS, our Selective Laser Sintering technology. These are actual air ducts used in Boeing aircraft. Most all commercial aircraft and or military aircraft have SLS parts flying in them today. Another great use for this technology is to create master patterns for castings. And this picture is an example of a RTV mold where we're using an SLA part to create the master pattern. And finally, another huge benefit of additive manufacturing is the ability to create custom tools and fixtures. This is a welding fixture used in aerospace to create custom tools, and it's utilizing our SLA technology. So the first production system technology that we're going to talk about today in greater detail is stereo lithography. What you see here is a full-size engine block. This is a master pattern for casting. I have some nice videos embedded into this presentation. Unfortunately, we learned that they didn't play very well in a webcast format. So we're going to make this presentation available to each attendee for downloading. And once you download the presentation, you'll be able to view these how it works videos. Now, SLA technology, and you would have been able to see this in the video, but you take a epoxy resin and you draw on it in a multi-directional way to create better than injection molded, highly accurate, highly precise parts that give you fine feature detail, true to CAD. One of the benefits of SLA is that you have very limited post-processing. Not all geometries require supports, but if you do have supports, they are easily removed. Not very limited amount of sanding, if any, is required. It's a no-waste process. All the material that is unused is fully recyclable and able to be used again. You have simple user selectable print quality. In other words, depending on how highly detailed or the surface finish resolution you're looking for can be adjusted where you are in the prototyping process. We have a very wide range of functional materials, and we'll go into that deeper later. And you also have the ability to change materials very easily. This touches on the accuracy that you can get print to print, machine to machine. You're looking at plus or minus 45 microns, which in tolerances of 0.002, which meets or exceeds most all injection molded plastic tolerances. And these are some photos that really show you the types of features and part resolution that you can get with stereo lithography. Now, I mentioned that we would go into a deeper dive into the materials. So depending on the type of product that you're prototyping, if you want a soft plastic polypro type material, you can do that with stereo lithography. If you want a more rigid ABS-like texture or toughness or tensile strength or elongation or break, you can do that with our ADS class materials. We also have a highly We have a highly durable class of materials, a clear class. You can actually get perfectly clear materials like glass. We have high temperature materials, for example, on those tools and fixtures for welding, and we have a number of specialty class materials as well. So typically you would work with Applied or with me or with one of the 3D Systems application engineers on material selection based on the types of properties that you're looking for in the final prototype. The next process that we're going to talk about is selective laser sintering. As I mentioned earlier, SLA is primarily used in prototyping, form, fit, function, fluid, dynamics type testing. You can get limited functional use. In fact, a lot of the automotive manufacturers use SLA to test a number of the components on an automobile, but they can only do so in a limited basis. But with selective laser sintering, what you're creating are truly functional parts out of a nylon-based thermoplastic. And this is the How It Works video that I encourage you to look at once you download the presentation. So SLS is going to give you the strongest, most durable printed plastic parts in the industry. Some people will try to suggest that FDM parts are stronger, but they truly aren't, because with SLS you're able to get strength in all three axes, the X, the Y, and the Z. As I mentioned, these parts are fully functional. They're currently in use in a number of applications today in automotive, aerospace, medical device, etc. And they can be used straight out of the printer. Long-term stability properties and dimensions. To go back to sustainability, this is a low waste, low carbon footprint alternative to traditional manufacturing. And it has strong environmental resistance as well. Can be used outdoor. It's not degraded by UV light, and it has a very wide temperature range, as you can see on this slide. One of the drawbacks to some of the earliest SLS technologies that you can't or couldn't get the fine feature, detail, and surface finish that you could get with SLA prototypes. But with our new technology, the ProX 500, we are able to get fine feature and detail and surface finish as good as SLA and or injection molded plastic parts. I think you would be very impressed with these parts if you had an opportunity to see them. As I mentioned earlier, these are production ready, very accurate parts, machine to machine, print to print. One of the benefits is SLS that no supports are required. You can actually nest parts within the build envelope. Our software will actually help you do that to maximize the utilization of each run. But again, there's no support material. There's no waste. They can be printed in any orientation. You have strength in all axes, and you can see the tolerances now are pretty incredible. Some of the advantages of additive manufacturing over traditional manufacturing, number one is it's going to save you money. You can do extremely rapid product iterations for prototyping. You can do mass customized additive manufacturing. It gives you unlimited design freedom in terms of geometries that you wouldn't be able to achieve through traditional manufacturing. No supports, as I mentioned earlier, which makes it environmentally friendly and obviously saves you money. There's very limited to zero post-processing, no support material. Most people can use these parts directly out of the machine. But if you wanted to dye them or paint them or plate them, you can do any secondary post-processing process that you could do on any other traditionally manufactured plastic part. One of the significant technological advancements that we've made with SLS is the amount of material recyclability. In the past, you were looking at maybe 33% virgin material in each build. Now we're looking at 20% virgin material in each build, and our competitors are still in the 50% range of virgin material on each build, which what that does ultimately is drive down your overall costs and improve your ROI. I think this is the best example to show the benefits of additive versus traditional. This is actually an aerospace part that's currently used today. The company that was building this particular duct, in the traditional manufacturing process, it required 15 parts, 5 different SKUs, 3 different custom tools, and 10 different assembly checks because it had to be approved by the federal government, either the military or the commercial aircraft regulatory bodies. Now, with SLS, we were able to build the part with all the required geometry in 1 part, 1 SKU, and 0 custom tools, and just 1 assembly check. So it enabled us to consolidate the parts, reduce labor, and eliminate tooling altogether. The next technology that I'm going to touch on today is direct metal sintering. 3D Systems got into DMS in a big way back in July through the acquisition of a French company, Phoenix Technologies. We acquired Phoenix Technologies and incorporated their products into our product line. We're currently in the process of rebranding everything under 3D Systems, and will also begin manufacturing in North America starting in May. Now, some of the key benefits of DMS is material flexibility. We can produce parts, or we have produced parts in 15 different materials. It is an open system, so there's no limitation of the metal or metal alloys that you could test or build parts with. We've just successfully built parts with 15 different materials, including steels, both tool steels and stainless steels, cobalt, chrome, reactive metals including titanium and aluminum. I could go on and on and on. But you get very excellent surface finish and high resolution. You get great accuracy and repeatability. And as I mentioned earlier, you get mechanical properties superior to a lot of casted or forged parts, and very fast build speeds. particularly when you're getting into complex geometries versus traditional milling or CNC type processes. And this is showing you an example of some of the different materials, anywhere from aluminum to copper or ceramics. The Phoenix technology, or now the 3D Systems technology, has by far the best surface finish of any DMS part produced today. Surface finishes down to 5RA, feature resolution at approximately 150 microns, very easy support removal with minimum scarring, and support requirements are very limited due to some proprietary technology that we have in the way the way we layer the material. Number one, we're using material down to 3 micron powders. We actually have some proprietary technology where we are compacting each layer, which makes the part bed itself or gives the part bed itself the ability to support a number of geometries that our competitors have to use mechanical supports. For example, these blades, these overhangs were self-supported. It would be very difficult in terms of secondary processing or post-processing to remove mechanical supports from this part without damaging these very thin blades. Very excellent tolerances and repeatability. As you can see on my slide, 50 to 100 microns in most dimensions. One of the things with all additive manufacturing, you can dial in your build parameters or your processes, particularly if you're going to be building the same part over and over and over, and that's going to improve your repeatability as well. But this part that I'm pointing to now is a piece that shows some of the benefits of the Phoenix technology. This is a 8,000ths post unsupported. This is a 10,000ths channel. This is a flange or an overhang at a 35-degree angle. And you can also see some of the incredible geometry that can be created. As I've mentioned a number of times, but it's worth repeating, we get mechanical properties superior to most casted or forged parts with theoretical densities over 99%. This is a good example of a chromium cobalt part directly out of the machine that's been lightly bead blasted, but you can also see it after it's been polished. It's a great demonstration of what you can do in terms of post-processing, polishing, plating, drilling, tapping, threading, anything that you could do on a casted or forged part. Very fast build speeds in comparison to a lot of the traditional methodology. Very high utilization. This build plate has over 250 tire sites. One of the really neat applications that is being rapidly adopted is in the tire industry. The creation of tire molds is very complex, very time-consuming, and very expensive, utilizing traditional methodology. What the tire manufacturers have learned with additive, that they can create molds faster, with more accuracy, and they're actually able to utilize geometries that are making tires more fuel efficient and quiet, and in terms of acoustics, and also tires that wear longer. It's really amazing how rapidly the tire manufacturers are adopting direct metal sintering. Another area, if you have very fine, highly detailed, small parts, you're able to sinter parts that you would never be able to do with traditional manufacturing. This is a great example of geometries, unsupported geometries, lattice structures that would be fantastic for use heat sinks and electronics and other applications. You can print things that you would never conceive of trying to do in the past, and it really frees up your designers to think about, there's really no limitations. They can, that goes back to that democratization. A lot of times designers think, well, I would really love to create a part that has these geometries, but I can't do that because it's not designed for manufacturing. You can kind of throw that out the window now. I love this part. It's an example. This is a true fuel injector that another customer has in production. They were able to improve fuel efficiency significantly by changing the angle in this injector, but that they weren't able to produce it with traditional manufacturing, and by growing the part layer by layer, they were able to do so. I'd like to focus the balance of my time on what we refer to as RED, or reimagining the engineer's desktop. So here are some of the components of RED. What you see here is a scanner. Here's a part. This is a haptic touch type device, and this is a ProJet 3510 multi-jet modeling printer. So in theory, what we're doing here is, if you have a part that you want to capture in 3D modeling software, instead of having to create the part organically, now you have the ability to scan the part, actually load it into your 3D CAD package or modeling software, manipulate or modify the file however you wish, including organic sculpting with a haptic device, and then actually print your prototype. So that goes back to your ability to speed up the prototyping process. This concept is really ideal for companies that may have legacy equipment, that replacement parts are very difficult to come by or very expensive to outsource. But now with 3D or additive, you can really do a lot of mass customization or create re-engineered parts. So this talks about the process: scan, import your model manipulate your model, print your model, both either as a prototype or a directly manufactured part, and then by utilizing your scanner again, inspect your part for the tolerances and repeatability. Now, these are some of the advantages of digital workflow. You can scan any object, whether it be a part, a tool, a clay sculpture, or anything that can be imported into 3D CAD modeling software. You can quickly capture complex shapes in a digital format that, as I mentioned before, that data, that model can be edited and changed as necessary or as needed. And the final data can be used for printing, sculpting, rendering, inspection, analysis, and digital archiving. We have some customers that are utilizing this technology to archive hundreds, if not thousands, of tools that are sitting on warehouse shelves that are just taking up space that can be repurposed or recycled or reutilized. And that's the end of my presentation. I want to thank you for your presence and listening to me. And at this point, I'll turn it over to Tiffany for questions.
Thank you so much, Daryl, for that presentation. Does anybody have any questions at this point? There were none typed in the question pane. Okay. I guess if there are no questions, then I would like to thank you all for joining us today, and we hope that you found this webinar informative and helpful to your design and or engineering practice. And as we said earlier, you will be receiving a link when this presentation is posted, and you may review any material you missed or simply want to go over it again. And we will be adding, then you will be able to see the videos there. And we would like to thank you for joining us today and taking time to view this presentation. So have a great rest of your day, and follow us closely on Facebook at facebook.com/livelablearning for any upcoming training opportunities. And you can also visit our website at livelablearning.com for a complete schedule of the upcoming and future webinars, updates, and more. So again, thank you, Daryl, so much for your presentation today. And if there are no further questions, then we'll go ahead and wrap up.
Thank you, everyone, for your attention.
Thanks, Daryl.
You're welcome.